So let's go over this. Okay, so look at the proposed mechanism for the top reaction first. Think about these equilibrium mechanisms, right? The reactions that can go both forward and backward. When you're thinking about the mechanism in one direction, right? You're going to be using the same exact starting materials, products, and intermediates as you in the reverse direction, right? So all of the molecules, all of the structures will be the same. You just have to rationalize different arrows that take you in the reverse direction rather than in the forward direction, right? So just like there are two mechanisms going from the carbonyl to the hydrate, there are going to be two mechanisms that take us from the hydrate back to the carbonyl. Right, so the first one that we can draw will show elimination of a hydroxy group. Right, so hopefully you can recognize this first set of intermediates as the first set of intermediates that we would see in the forward reaction, right, the hydration reaction. All we're doing is just rationalizing how we get from product back to the starting material, right? So the arrows that we draw are going to be different. Okay, so just like we can draw a mechanism, hydration mechanism, as a two-step mechanism, we can draw the dehydration mechanism also as a two-step mechanism featuring the same set of intermediates. Right? Something I'll point out here, you'll see when we start this reaction, the net charge of our reactants, the hydrate, is neutral. Right? And when we end this reaction, the net charge of the product is neutral. Right? The intermediates have to adopt that same net charge. Right? So you can create intermediates that have formal charges, but if we're starting with a neutral compound, those formal charges that are created have to cancel each other out, right? We can't just all of a sudden create a charge for no reason, right? So if we're starting with neutral compounds, we're ending with neutral compounds, and all of the intermediates have to be net neutral in between. Okay, any questions about that mechanism? So remember the second mechanism that we went over when we're thinking about the hydration, there's going to be a molecule of water involved in shuttling a proton between two different oxygens, right? Because this process cannot happen intramolecularly, it has to happen intermolecularly. And so we're going to use that same molecule of water when we draw the second mechanism. So the first step we'll show is deprotonation of one oxygen. Formation of a hydronium acid. All right, so water got an extra proton, and then we're going to transfer that proton to the other oxygen. Going to get us to this intermediate, and then this will just undergo elimination, reform the pi bond, and kick out our molecule of water. And that gets us to our products. you look at this mechanism, right, this is the dehydration mechanism. This would be the equivalent hydration mechanism, right? Here the reaction is occurring to form a ketone, right? Up here I'm showing an aldehyde reacting with water, but it's the same mechanism, right? We're focusing not on the fact that we have a ketone or the fact that we have an aldehyde, but the fact that we have water interacting with the carbonyl, right? That's the only thing that matters here, right? So you can see that these intermediates, whether we're going in the reverse direction or in the forward direction, are going to be the same, right? So here the product is a carbonyl and water, right? Up here we're starting with a carbonyl and water, right? As we move to the second to the last intermediate here, right, you can see it looks exactly the same as the first intermediate up here, right? We have a molecule of water, positively charged oxygen attached to that carbonyl, right? And then a negatively charged oxygen. Same thing up here, molecule of water with a positively charged oxygen and a negatively charged oxygen. As we move over here, right, in the reverse direction, the second intermediate is going to be the same as the third intermediate up here. So we have an OH group, an O minus group, and a hydronium, an OH group, an O minus group, and a hydronium. Right, so the intermediates going forward and going in reverse are going to be exactly the same. Right? It's just a matter of how you rationalize the electron movement to get to the next step in the mechanism. All right, questions about that? Questions? Okay. All right, so the second thing I wanted you to do was see if you could draw an energy diagram for this mechanism. All right, so this is the forward hydration mechanism. When we look at this mechanism, you can see that there are going to be 1, 2, 3 steps of this mechanism, right? So each arrow is a step in the mechanism because it represents going from these things to this thing. Okay, so that's one step. And so when we represent that, we'll say that this is A, B, C, and D. When we draw this on an energy diagram, right, those A's, B's, C's, and D's are going to be the lines, right? That's what we're focusing on for the thermodynamics of the reaction. Right? This is the energy of A, this is the energy of B, this is the energy of C, this is going to be the energy of D. Okay? Now I wrote up here that I said assume a KEQ equals 1. How is that, how do we show that on a reaction energy diagram?
Is that shown by the fact that A and D are the same energy?
Awesome, yeah, perfect, right? So if the KQ is equal to 1, we would expect the energy of the starting materials to be the exact same energy of the products, right? So there's going to be a 1-to-1 ratio of those two things once this reaction reaches equilibrium. Right? If the KEQ is between 0 and 1, then D should be higher than A, right? If the KEQ is greater than 1, then D would be, this would be an exothermic reaction, right? And D would be lower than A. Right, questions about that? Yeah.
So if you were to draw an energy diagram for the reverse of that equation that you just drew before, so like the top equation using the first mechanism, is there only one transition state?
So yeah, so good question. So if we were to draw an energy diagram for this,
The one above it. Like,
for
yeah.
this, yeah, so there would be 3 lines and then 2 steps, 2 transition states.
Okay. So
Okay.
1 intermediate and 2 transition states.
1 intermediate, 2 transition states. Yep. Yep. So each of the steps here, 1, 2, and 3, right? That's going to be represented by a hump, right? So. Right, this would be transition state 1, right, or step 1, transition state 2, and transition state 3. Very good.
How do you know B and C are equal energy?
It's a good question. If you look at those two, why might they be equal in energy?
two molecules?
I would say, so they both kind of feature the same, same charges on the same atoms, right? So here we have a negative oxygen, positive oxygen, and a neutral oxygen, right? Here we have a negative oxygen, positive oxygen, and neutral oxygen, right? Are they going to be the exact same energy? No, right? But as we're approximating or suggesting an energy diagram, we can say they'll be about the same, right? And they'll certainly be higher in energy than either of those because of that charge separation. Other questions? Yeah.
Are you able to know the rate limiting step of your transition state, or is that with numbers that we can't tell?
So we can determine the rate limiting step based upon the mechanism that we're showing here. Is that what you're?
No, I was gonna say, how did you determine the height of each peak? I'm sorry if you already said that.
Right, yeah, so that's the rate limiting step, right? So, Gianna, which step is the rate limiting step, as I've drawn it here?
It would be the first transition state.
Good, right? So this first step is the rate limiting step. Right, so that's the step that happens least frequently, is hardest to achieve, right? We have to put the most amount of energy in order for those molecules to interact with each other. Right, we talked about this at the end of class on Wednesday. So why would step 1 be higher in energy or require more energy to occur relative to step 2 and 3? Yeah.
Is that because you created charges in the?
It's not because of the charges, no. Yeah.
Is it breaking a pi bond?
The pi bond has something to do with it. Yeah.
Is it because the flow of electrons aren't like right with each other?
It's not. So when we talked about this the other day, right? We looked at how these molecules have to interact, right, in order for that reaction to take place. And so for step 1, try this out quickly. Right, for step 1, as that water approaches the ketone, right, the orbitals that have to overlap are going to be the filled non-bonding orbital on oxygen, right? So this is going to be sp2 non-bonding, right? And that has to overlap with the pi star orbital of carbonyl. Okay, I represented this methyl group as just kind of a straight line, but remember there are 3 hydrogens coming off of that methyl group. Right, there are going to be 2 hydrogens coming off of that ethyl group and then 3 over here. So there's a lot of electron density that we don't necessarily illustrate around that carbonyl carbon. Right, so if we think about those 2 molecules trying to push together in order for those orbitals to effectively overlap, it's going to be a lot harder because there's a lot of electron density that's going to be interacting with each other as we try to push them together, right? The antibonding orbital that we have to interact with on the carbonyl is a lot more hidden, right? Harder to get to than the antibonding orbital that we would have to interact with during acid-base chemistry, right? So for acid-base chemistry, in acid-base chemistry, the orbitals that you're interacting with are always going to be sigma antibonding orbitals to hydrogen, right? This is one from oxygen to hydrogen. You can have acidic protons on carbon, you can have acidic protons on nitrogen, right? There are other atoms that can contain acidic protons. Point being is that the antibonding orbitals, if you're interacting with the hydrogen, hydrogens are always going to be on the outside of the molecule, right? Just based upon the bonding patterns of hydrogen, right, where we find them. And as a result, the antibonding orbitals that we have to interact with are going to be on the outside of those hydrogens, right? So even further on the outside of the molecule. So when we think about two molecules coming together, it's going to be really easy to interact with the sigma antibonding orbitals on the outside, right? So these molecules don't have to have their electrons bumping up against each other so much. Here, when water comes in, right, that water has to maneuver past these hydrogens over here, maybe some electron density up on the oxygen, right? So it's just a much harder orbital to reach. And so when we think about that, right, that's reflected in the amount of energy needed to push those molecules together, right? It's not magic when molecules react. They actually have to, be next to each other and interact. We're not just pouring stuff in a flask and closing our eyes and saying, poof, it's magic, right? They actually have to be able to interact with each other. And if that's hard to do, like it would be up here, right, then we would expect more energy needed in order to force those molecules together so they can interact, right? And if it's relatively easy for those orbitals to overlap, right, and that's going to be reflected in the energy of that step. Right? There's not a whole lot of energy needed to force those molecules close enough to interact with each other. Right, and so that's how, the exact level of activation energy, I'm not expecting you to be able to determine that, but I expect you to be able to look at a reaction and say, okay, this step is probably going to be a much higher energy step than these other steps, because these other steps are just acid-base steps. All right, so we can determine that here just by looking at the mechanism and seeing, well, here we have to add to a carbonyl carbon. All of these others are just proton transfers, so they should be pretty easy to do. Yeah.
So for the carbonyl, when you react with it, do you always react with the antibody?
So just like in order to break a sigma bond here, we have to put electrons into the sigma antibond, right? In order to break this pi bond, as we're showing here, the electrons have to be put into the pi antibond. Other questions? Okay. All right, so I want to introduce you to a couple of terms that we're going to be using from here on out. Right, and those terms are nucleophile and electrophile. Right, and we use these terms like we would Lewis acid or Lewis base. Right, but let's try to understand what they mean. Right, so when you break down the word nucleophile into its prefix and suffix, what do you think it means? Yeah, right.
Something that wants, well, so nucleus most file is it wants to.
Good, good. So we can say that this is nucleus loving. Right, and I'll put a positive next to the nucleus, because hopefully everybody recognizes that the nucleus is positively charged. Right, and then what about electrophile? Yeah.
Electron loving.
Awesome, electron loving. Right, so something that wants electrons. Okay, and so when we look at how these two molecules are interacting, right, the electrophile, the electron-loving molecule, is the thing accepting electrons from an outside molecule. Right? And the thing that's donating those electrons is the nucleophile, because it's attracted to the positive nucleus of whatever atom's on the electrophile. Right? So we can define these terms loosely using the Lewis acid and Lewis base definitions. Right, so a nucleophile is the same thing as a Lewis base, right? Just an electron pair donor. An electrophile will be a Lewis acid, which is an electron pair acceptor. Right, and we're going to distinguish this from the Bronsted acid base, right? So we're gonna consider Bronsted acid base as Bronsted acid base, right? Things interacting with protons, so proton donor, proton acceptor, right? Nucleophile, electrophile, we're going to consider when there are bonds being made and bonds being broken that are not protons, right? So we would consider this oxygen a nucleophile, and this carbonyl, or this, the water a nucleophile, and the acid aldehyde an electrophile, right? Over here, we would consider water as a Bronsted base, right? And this is the Bronsted acid, because the step that's occurring is just a proton transfer, right? So if we're making carbon-carbon bonds, carbon-oxygen bonds, carbon-nitrogen bonds, then we would call that step nucleophile electrophile. It's just a proton transfer, it's just a Bronsted acid-base reaction, then we'll define it as an acid base. Okay, questions about that? Yeah?
You said that if it's a proton transfer, then it's Bronsted.
Yep.
But electron transfer, it's
No. No, well, yeah, if we're making carbon-oxygen bond here,
okay.
right? We would consider that nucleophile electrophile.
Mhm.
Here, this is just making an oxygen-hydrogen bond and breaking an oxygen-hydrogen bond, right? So that's just transferring a proton from one atom to another, right? That's just Bronsted acid-base chemistry. Right, so nucleophile, electrophile, right? We can recognize them based upon what the electrons of those molecules are doing, but we're going to define them based upon what bond is being made, right? So I wouldn't consider this a nucleophile, an electrophile. I would identify that as a base and acid. Right here, there's no proton being transferred, so I can't identify this as a Bronsted acid-base reaction, right? It's a Lewis acid-base reaction for sure, but we're going to further refine those terms to use
So
nucleophile.
it doesn't include the transfer of that proton. Okay.
Yep. Other questions? Okay. All right, another term that you've seen before, but we're going to apply slightly differently, is if we look at this step, so this is the nucleophile here, water, the electrophile, and the carbonyl. Right? Each step of this mechanism is going to have, we can name the orbitals involved. Right? And so the nucleophile is always going to contain the highest energy occupied orbital, so the highest occupied molecular orbital. And in this case, it's going to be the sp3 non-bonding. Orbital on oxygen. Okay, and just like we have a HOMO, there's also going to be a LUMO. And the LUMO will always be associated with the electrophile. Right? And in this case, the LUMO is going to be the carbon-oxygen pi antibonding or pi star orbital. Okay, so in a reaction, the HOMO is the orbital that is donating the electrons, right? And specifically the orbital, right? So we're not naming this molecule is the HOMO or the oxygen is the HOMO. right? HOMO refers specifically to an orbital, highest occupied molecular orbital. And so when you're naming or identifying the HOMO, you have to name the orbital. Okay, in this case, it's the non-bonding orbital, sp3 hybridized on oxygen, right? Same thing down here. The HOMO is not the ketone, it's not the carbon, right? But the orbital that's being interacted with. And so the electrons are going into this empty pi star orbital on carbon. And so that's how we would identify the LUMO. Any questions? Yeah, correct.
So you said HOMO is always a nucleophile?
HOMO is always the nucleophile, right? Because that's the molecule that's donating the electrons. And so that's where the electrons are coming from. The electrophile is the molecule that's accepting the electrons, so that's where they would be going to. Other questions? All right, anybody have any questions on this energy diagram before we move forward? Yeah.
I have a question about the LUMO.
Yep.
So, what orbital would it be the antibonding orbital that is the LUMO, or is it?
Yeah, the carbonyl pi antibonding pi star orbital. Right, so the one pi star orbital is represented by these four lobes here. Right? And this is the atom. I've kind of drawn the coefficient a little bigger here to show that's the atom that wants electrons more. Right? So when the water approaches, it's going to approach either from this top face, right, or it could approach from the bottom face. Right? But that's the orbital that the electrons are being put into, the empty orbital, right, or unoccupied orbital.
So it has to be empty or unoccupied to accept
Yes.
the electrons. So we would identify which empty orbital it is.
Right, right. In most cases for this chapter, the LUMO is going to be the carbonyl pi antibonding orbital, right? In a lot of cases, for a lot of reactions, the orbital, LUMO orbital is going to be an antibonding orbital, but not all cases, right? So there are some reactions that can occur where the LUMO is an empty p orbital, right? It's not antibonding, but it's still empty. So it just needs to be an empty orbital, whether it's antibonding or otherwise. Makes sense?
Yes.
Nucleophile is always the HOMO, or is it just in this?
The nucleophile is always going to have the highest occupied molecular orbital, right? They're not the same. Nucleophile is a molecule, right? The HOMO is an orbital on that molecule that holds the electrons that are forming a new bond, right? But the highest occupied molecular orbital will always be on either the nucleophile or the base if it's an acid-base reaction. Yeah.
I just wanted to be clear, so the HOMO orbital on the water molecule is the one with the electrons in it, correct?
Correct, yeah, I mean, there's a pair of electrons here as well, I just didn't draw them in.
That's the sp3, not an sp2 then?
That's an sp3 orbital, yep.
Okay, it says sp2 on the board and I was a little, like with the non-bonding.
The other
Like,
side.
the other, in the purple.
Oh, sorry.
Yeah,
Yeah,
it's okay, thank you.
yeah. Anything else? Okay, so next I want to talk about catalysis. Actually, you know what, let's talk about equilibrium instead for a second. Okay, so here are three reactions, right? All hydration reactions. You can see in the first reaction, we're starting with, the carbonyl that we're starting with is formaldehyde. Second reaction, the carbonyl that we're starting with is acetaldehyde. And then the third reaction, we're starting with acetone, right? So we're changing the structure of the carbonyl just slightly as we go through these three reactions. Okay, I've shown you the direction of the equilibrium. All right, but let me give you some numbers here. Right, so the KQ of the reaction up top is 2,208. Right, so much greater than 1. It's indicating that this top reaction is product favored. Right, and we can quantify it by saying when this reaction reaches equilibrium, there are going to be 2,280 molecules of the hydrate to every 1 molecule of the aldehyde. Okay? So it's going to prefer being in this state, in the hydrate state. Okay, if we replace one of those hydrogens with a methyl group, and now we have 1 hydrogen, 1 methyl group, now that KEQ of hydration is going to be equal to 1. Right, so that means that there's going to be 1 hydrate, right, for every 1 molecule of the aldehyde. So this is a pretty well-balanced reaction. Right, so when it reaches equilibrium, we'll have an equal number of hydrates and aldehydes. Right, and if we take the other hydrogen off, and now we have 2 methyl groups in acetone, okay, now you can see that that shifts the equilibrium to the left. Right, so now KEQ is 0.001, that means that we have 1,000 molecules of ketone to every just 1 molecule of the hydrate, right? So in this reaction, these two things are reluctant to react with each other to form the hydrate. Right? How would we show that on this energy diagram? Right, so say that all of these are kind of starting at the same energy level. Okay, this we already established represents the acetaldehyde. If we wanted to represent the other 2 reactions on here, where would we put them? Yep.
In the first reaction should be hexagonic, so D would be lower than
Good.
A, and last reaction would be endergonic, so it would be higher.
So, oh, this is the hydrate, not that. right? So if the molecule is exergonic, that means that this is going to be a more stable product. And so we should put that lower down on the energy diagram, right? Here the reaction is endergonic, so this should be less stable than what we expect up here, right? So that should be higher up on the energy diagram. Okay, everybody's all right with that? Right? Okay, my question is, I always loved asking this question, why? Right? Why is this going to be, got an oxygen here. Why is this going to be lower in energy, right? Creating a favorable hydration reaction, and this is going to be higher in energy, creating an unfavorable reaction, right?
There's less stuff around the central carbon.
What's that?
There's less stuff around the central carbon, so like there's less electron cloud.
Okay, why does that matter?
Because the closer in proximity that the negative charges are to each other, the more they have to work to stay with.
Okay. That's all true, and you're heading in the right direction. Need a little more detail though.
You made a fool of me.
What's that?
You made a fool of me.
A fool of you? No, you're not a fool. Anybody else want to add something? So what's Frank? I'll stick with you. So if you look at the starting material, what's the geometry of the central carbon in the starting material?
Trigonal cylinder.
Okay, what are the bond angles around there?
120.
Okay, and when we go to the product, how are we changing that?
Is you change it to 109.5.
Good, right? So we're taking bonds that are like this, and then we're adding a substituent and pushing those substituents that were already there together. Okay, that's not a problem if those substituents are hydrogen, because hydrogens are really small, right? And we can push them together. We can narrow those bond angles from 120 in the starting material down to 109.5 without much consequence, right? The reason why this would be exothermic is because we're getting rid of a relatively high energy carbon-oxygen pi bond, and we're replacing it with a relatively lower energy carbon-oxygen sigma bond, right? So enthalpically, this is good, right? Down here, we're doing the same thing, but unfortunately, we have these two big methyl groups that we're starting with at 120 degrees, and when this reaction is ending, right, we're pushing those two methyl groups together, so now they're closer together, those methyl groups are interacting more down to 109 degrees, and so there's going to be more steric interaction, more electron interaction here, right? And this is not going to want to form the hydrate, right? So what we can pull from this is that in general, aldehydes we think of as better electrophiles than ketones, right? Because if we add something to an aldehyde, it's going to be easier for it to adopt a tetrahedral state, to push those existing substituents together, right? And harder for a ketone because the groups around the ketone, being carbon, necessarily have to be larger. Right, so the structure of the starting material is going to influence the equilibrium of these carbonyl addition reactions. Very good, Frank. All right, I'll see you guys Monday.